right now. So specifically, I was assigned to design a Python code. However, is we have a different issue, so this was later on failed. So first, we have to find out what is an FIR, which is a finite impulse response. So as you can see that a digital filter, we change a signal to keep the parts that we want and remove the parts that we don't. I will elaborate further on this on what this means. And a low pass filter lets low frequency changes through and blocks high frequency ones. So an FIR filter uses a fixed short set of numbers, and we can see that it is always stable and keeps us signal in shape. So mathematically, if we receive two signals denoted as xn and yn, an FIR filter of order n is expressed as shown. So designing a low pass filter and low pass FIR filters, in order to do this, we need to find the HK so that the output keeps the desired frequencies, and also a cutoff frequency is chosen. As I've stated earlier, we need to remove the parts that we want. So frequencies below this value are allowed through, and higher ones are blocked. So the ideal filter passes all frequencies, as you can see right there, and we use this an inverse Fourier transform to truncate and shift the sync function to make it usable. And like I mentioned, a common way to build an FIR filter is we need to truncate the ideal impulse response to a fixed length. And then we will need to multiply this by a window function Wn to reduce the unwanted ripples in frequency response. And we can have common windows include the Hamming, Henning, and Blackman. And as you can see on the screen right here, we have a Hamming window which looks like shown. And using this method, we can give a practical FIR filter with a smoother and more stable frequency response. And so since the original impulse response is centered around zero, which means it uses future values and it is not really practical in real-time systems. And in order to fix this, we need to shift the response by n times and divided by 2 samples to the right. And this adds a small delay, but still it makes the filter casual. So next we need to move on to the next slide, which is about hardware components. We mainly use two components here, which is ESP32 and IMNP. So the ESP32, it acts as a CPU, and since it is powerful and pretty practical in this project, it has some key features such as I2S, which interface in order to connect it to the INMP 441. So next is since we have like many CPUs to use in this project, but we decided to choose the ESP32 because it can receive raw digital audio data from the INMP 441, and then it proceeds and applies a low pass filter in real time. So moving on, we have the INMP 441 as stated like twice in the previous slides, and it can perform in digital MEMs microphone with I2S output. So the main reason we choose this is in order to receive the audio input for the microcontroller-based systems. So here's our breadboard diagram since we only use like two components, as I stated earlier, which is the INMP 441 and the ESP32. As you can see right here, we connect the wires as shown. And here are the pins that we've also noted down in order to, avoid any confusions, because the breadboard diagram alone, we cannot fully understand how it is connected. So we have made this table for you to clearly see. So next is the implementing part.
So to design our bandpass filter, we use MATLAB Filter Designer, which provide a graphical interface for creating and analyzing filter. And we use filter size FIR, and the sample rate is 44,100, and the lower cutoff frequency 80 Hz, and the upper is 10,000 Hz. However, the first we need to do is 20,000 Hz, but we can simulate the sound up to that rate. So we put in here is 10,000 Hz to simulate that. And after configuring these parameters, we analyze the resulting filter response using MATLAB built-in plotting tool. And you can see here we using a Hamming window. And to explain why we use that, this slide helps us understand why we use the Hamming window. You can see on the left side, we see the time domain plot of the window. The smooth tapering of both end sides is the key. It minimizes discontinuity, which in turn divide ripple in the frequency domain. And on the right side, yeah, sao slide trên này khác. And on the right side, we see the frequency response of the window. And the main lobe width is about 0.0625. And this controls the resolution. Narrower the main lobe mean better frequency selectivity, and the side lobe level is approximately minus 42.2 decibel, much lower than for rectangular window. And lower side lobe mean better suppression of frequency outside the passband. And here is the ratio between the frequency, magnitude response and phase response. You can see in the first graph, the slope is the more rectangular it means the more efficient, and but it also means that it's more delay because the signal need to be go down. If the slope is larger, and mean the delay is also larger. And here is the ratio between both graphs. And next, we look at the input response, the time domain characteristic, which give us additional insight into the filter behavior. And here is the filter coefficient in the formula we give you before. It means the parameter of 8x.
So as we receive the filter coefficient, next we use the ESP33 and the INM for B441 to record the audio signal. As you can see here, we take it reference from Lương Hữu Phúc, and we modify by Grok. And we use the library I2S and also the FreeToast. And here you can see is the configuration. Here is the setup for the direct memory access length, as you can see here, and then the buffer size is also configured in here. Here is the clock configuration, and here is the read INMP441 data task. So to implement this, we need to install the ASP IDF development environment first. Then we set up the environment as follow. We need to configure it also, and build and flash and monitor in order to conveniently receive the data set. We use the application PuTTY, and you could set up as in here the zero with we pick 0, and through the 0 line the speed is recommended in here, and and also press on locking, press the printable output, and then choose the log file name and open. Then the monitor will resolve the signal that is received from the INP 441. The result is automatically saved to this file as you set up previously. Then we use the MATLAB to apply the low-pass filter from this dataset. And we also brought it by the time domain plot, the frequency domain plot of the original signal, the power spectrum plot of the original signal. We use the coefficient as we get from previously in here. And we filter the signal plot. Then also we have the same time domain, frequency domain plot, and power spectrum also. So as you can see here, the result, here's the original signal in time domain, frequency domain, and power spectrum as we receive it. And here is the filter signal. And this is the difference. As you remember in the previous past task, I have shown the the result we have in here is quite similar to what we initially want to get. As you can see here, here is the frequency at 10,000, and that is how it cut off. Here is the result that we zoom in. So next we apply the filter using the Arduino. So we use the same setup configuration and also the same coefficient. Here and here's the result. As you can see, we use the order of 42, which is quite normal, which is great for the filter quality. But however, the time delay of the filter is quite large, as you can see in here. The time delay is a big problem. But in some lower frequency, the time delay is not large as large as in the 10,000 hertz frequency. So in conclusion, we have successfully implemented low-pass filter in real time by using the Arduino. We use the MATLAB filter designer to calculate the coefficient and use MATLAB to implement it. And also we use the ESP32 and INMP 441 to receive the audio signal. But however, we have some obstacle in here. As you can see, we cannot recover the audio signal since the ESP32 does not have enough memory or transmission speed to accurately record the signal, and each zero print it also takes several hundred microseconds, which is a really big problem. And we also cannot create or record sound above 22,000 hertz on most devices because of Nyquist limit. So that's why we choose to implement a low-pass filter from to up to 10,000 only. So in the future, what suggestion? We suggest that we use the STM32, which and also an SD card to have the higher high frequency audio signal, to receive high frequency audio signal. And also we have the sampling rate up to 192,000 hertz, and we can capture the procedure ultrasonic signal and store them in the SD card. That is my suggestion, and that is all for our presentation. Thank you.
Bọn em là bộ lọc số nên là mạch em chủ yếu dùng để thu tín hiệu, còn